I will only very briefly discuss what algebraic problems I've worked on, and these will usually be related to computer science problems, and some even have applications which are important in computer science. Um, so, so I have to start with what is computing. Uh, so some history here. Turing basically mathematically modeled for the first time computation. Before that, it was thought in a very vague fashion as some process. But Turing said that it's actually a mathematical concept. So for that, he designed this, which we now call a Turing machine. So there is a control here which has only finitely many states, and the pointer here, it moves from one state to the next, from start state to intermediate states to the halt state. So Q0 to H. And then there is this, you can say, the kind of a primitive hard disk. So it is mathematically just an array which is infinite, where the finite control can actually, through this, it's called the head. Through the head, it can either read a cell, or it can write on a cell, or it can move in any direction it wants. Okay, so what this does is that it gives meaning to both time and space. Okay, so in computation, time means how many steps did the finite control work for before reaching the halt state, and space because how many finitely many cells were actually used. Obviously, in practice, there will be no meaning of using infinitely many cells because you want your process to end, right? So this is what computers are mathematically, and this is what an algorithm also is. So Turing defined this in 1930s. This is a very simple and most general mathematical model. It covered all other models that were defined before him in the beginning of 1900s. So we call it TM. And what is an algorithm? So algorithm for this talk will be the same as Turing machine. Okay, so whenever I say algorithm, if it is not clear what it is, you should just think of this machine, which these days is just computers. But when Turing defined it, there were not really computers. So it was an abstract thing that he defined. But obviously our real life computational devices follow this pattern. So what is the pattern? The pattern is that it's very much like a computer program. Which means that it is highly iterative and every step is trivial. Okay, so your computer, if you look at a screenshot of a millisecond, what it does is something very trivial. So it is just a collection of millions of trivial steps, and obviously you know that when you reach the end, something very non-trivial has happened, right? So the whole goal is to take very trivial steps, but reach some place which is very hard, at least to do it manually by hand. So this is what computers and Turing machine and algorithm is in this talk. So, but I will switch gears here. So instead of looking at this model, which is good for mathematical modeling, uh, what I am interested in is actually circuits. So circuit is a more algebraic model. I mean, as you can see, there is no algebra here. This is more of a flowchart. Uh, but to study problems in terms of resources, that okay, how much time your problem should take, how much space it will take, and whether it's even solvable. Um, what is more helpful is actually to have a more algebraic model. So for that, we'll take inspiration from electronic circuits, and it's algebraically better to study. So let's move to that now. So this was formally done by Valiant. Um, and I call it, I mean, he called it algebraic circuit. So it's not electronic, but algebraic circuit. They are very similar. So so Valiant formalized computation and resources in terms of algebraic circuits. So what is that? It is it's basically variables are there, or the input is there in the leaves, and then in the intermediate layers you have gates or operators, which are in this case will be addition and multiplication. So you can think of an addition gate or a multiplication gate as a microprocessor chip. Okay, so it's a fabricated chip. It takes two inputs, and then it can add or multiply, and then it can give an output, and then it is fed to the next chip. Okay, so you have to fabricate this whole thing, and then the result is the output, right? So in this case, you can see that it's computing x plus y plus 10 times w times y. So it's a polynomial. If we think of the input as variable, algebraic variables, then what you are really computing is a polynomial. So this is more of a functional uh, computational device instead of simply input output, right? So the whole function will be actually computed in the end. So it's algebraically a much better thing to study. And what are the resources here? So the resources here are what are the constants you are using on the wires. Like for example, here you are using 10, right? So 10 comes from the string of integers. So those are the constants. Variables are how many variables there were. So there were 3 variables, trivariate. And what is the size of the graph, right? So how many edges are there, how many vertices are there. So that is the size. So size is the most important thing you want to optimize, right? Because you don't want to fabricate too much, you don't want to spend too much time in going from the leaves to the root. So that is called depth. What is the longest path from the leaf to the root? But more important in a way is the size, because you don't want too many microprocessor chips to be needed to compute this polynomial. So now the question comes, what are the polynomials which will take small size and what are the polynomials which will take big size, right? So the question is about resources and question is about efficiency or hardness. So that is the hardness question. So because of this model, there is this central open question in computer science, which is P and P, and we are now asking here variance P versus variance NP. It's, I mean, I don't want to go into the actual meaning of this, but the question is there, can you think of a polynomial whose coefficients are simple to describe, but the polynomial will take a very, very big circuit if you wanted to compute it in practice? Okay, so simple to describe, but hard to compute. Are there such polynomials? So this is the question of algebraic hardness.
So do you mean the depth or the total number?
The size.
The size.
Yeah, size is the most important thing. Everything else is extra. Yeah, but since you asked, so depth is basically in practice time. The depth corresponds to computers' time and size corresponds to how big the computer is. Because the bigger the graph is, it means that you need more chips. So that's a one-time investment. Yeah, so this figure may not mean much for most of you, but this is just a hypothetical construction. We don't have proof for this currently. All these are open questions. So there are these classification of problems or collection of problems like formulas, variance formulas, variance polynomial time, and variance NP time. And the question is whether these things are actually separate. Okay, so whether there is an actual gap between these polynomials or whether they are all the same. So these are open, the main open questions. We expect a gap because we expect that nature has hardness. So there are polynomials that are easy to describe, but they will be very hard to compute. Okay, just because we think that nature is adversarial, we draw the graph, we draw the diagram as this, but we don't have mathematical proof. These are the open questions. Some of the questions I'm interested in. So let's look at a simple problem to state about circuits in which I have spent an enormous amount of time and I've still not solved it. So the question is, you are given a circuit like the picture you saw before and you have to check whether it is zero. So what does it mean? It means that it takes variables and then it does a lot of computation, but ultimately what it gets is the zero polynomial. Okay, in other words, your circuit is an identity. So this question is called polynomial identity testing question, or in short PIT. Why is this important? Well, suppose I throw this big giant identity on you, right? So there are 8 variables and the degree of the polynomial on both sides is 4. Um, and I claim that this is an identity, right? Now if you are in the audience and you are awake, you will not believe this immediately because there is so many things happening. So the only way you know is you multiply things out and then add them and see that everything cancels and you get 0 or you get A equal to A, right? So is there a faster way to do this? I mean, you can do this manually in few minutes, but then I can give you bigger and bigger identities, and at some point your patience will break, right? So at that point, what will be your algorithm? So that is the question of PIT. Is there a fast way to check identities? Uh, and so this is the famous Euler's identity, which is used to prove Lagrange's four-square theorem. It's historically very important. So based on identities, there are many algorithms or mathematical problems or even computational problems which are related. So I'll just give a list of these which I have worked on and I'm still working on. So first is primality. So primality is the question whether a given number n is prime, right? So believe it or not, it is the same as asking this question. Okay, so you are given a polynomial x plus 1 to the n and you are given x to the n plus 1, whether they are the same polynomials when you divide by n. Okay, so mod n is simply computing the remainder. So for example, day 1 and day 8 are the same days, right? So there the modulo arithmetic is mod 7. So similarly, this polynomial and this polynomial, they look the same when you divide by n. Yeah, so this actually is a criterion for primality of n, right? I mean, you can take it as a homework exercise. So based on this, we actually gave the first deterministic polynomial time algorithm for primality. And that really is a general question for PIT. So the open question is whether PIT can be solved in, I mean, let me first say, can it be solved efficiently? And then the technical question is, both these keywords are important. It should be polynomial time, which is a notion of efficiency, how fast, and deterministic, which is the notion that you have to solve it correctly. You are not allowed to use coin tosses. Okay, so if, I mean, your computer say cannot toss coins, it can only do deterministic computation. So on a computer, can you solve PIT efficiently? So primality, because of this identity being very special, we can solve it. And then for other models also, we have some algorithms for PIT which are called black box algorithms. And we have some results about identities in terms of geometry. So we, in some very special kind of models of circuits, circuit identities, we identify what is called incidence geometry, and we give results based on that, which ultimately become actually independent of the field. So they work not only over the real field but over finite fields and so on. So we have those results. We have some properties of circuits which we have invented because of PIT, like duality. And the final point here is bootstrapping. So bootstrapping is that we have shown results where we study very tiny circuits, and we show that if you understand them enough, then you will understand also bigger and very general looking circuits. So the connection between very small parameters and general parameters. Okay, so it's called bootstrapping property, and we have identified a number of models which by themselves they look very special, and the parameters are very simple, very small. But if you solve PIT for them, then you will solve it in general. Okay, so these are the structural results and the problems, which are, most of them are still open problems, but we know them for special cases. So in general, this PIT problem motivates new tools to study algebraic computation. Okay, this is an important motivation to do PIT. And now I'll move to some algebraic algorithms which may or may not be related to circuits, but they are still important. So the problems I'm interested in computational algebra. So the first problem is the famous 3-century-old Newton iteration. So if you recall, Newton iteration is the problem of given a real curve, you want to find zeros, the roots, right? So the way Newton did it was to start from some random location on the curve, and you draw a tangent, and where the tangent intersects the x-axis, you go there, look at the corresponding point, and proceed, right? So, and he showed that at an exceptionally high rate, you will converge to a root, right? The root being the black point here, uh, or the red point, in fact. So at an exceptionally fast rate, you will actually converge there, but there are some conditions which is very important, that it only works for simple roots. So the root which is this red point, its multiplicity should be 1. Okay, for example, x square equal to 0 has multiplicity 2, x equal to 0 has multiplicity 2 there. So in those cases, it will not converge, it may actually diverge somewhere else. But as long as the root is simple, you actually reach that real root and you can compute it at whatever accuracy or precision you want. So we generalize this to non-simple roots, and not only that, but the multiplicity can be exponential, and we do it at the level of circuits. Okay, so we basically gave an algebraic or circuit analog of Newton iteration, removing as many preconditions as possible, and that is related to a big area in computational algebra which is called factoring polynomials. So what is the question of factoring polynomials? So for example, if I give you x square minus 2, a factor of x square minus 2 is essentially computing square root 2 question, right? So
You have 3 minutes, sir.
okay, so suppose I give you x square minus 2 mod 7, can you factor it? So the question is, you have to basically find square root 2's expansion in terms of 7. Okay, so it's a strange power series, because you see that the numbers here are increasing, but there is a mathematical way to still make sense of it. It's looking at square root 2 mod 7 square, mod 7 cube, and so on. So this is in number theory called 7-adic, in general p-adic. So I'm interested in factoring polynomials modulo primes, modulo prime powers, and modulo and over p-adics. Okay, so many questions there. I'm interested in finding approximative roots. So for example, if I give you a system x equal to 0 and xy equal to 1, you can see that there is no solution, but there still are approximate solutions. For example, you can take x to be 0.001 and then you can take y to be 1000, right? So given a system, finding approximate solutions. So for that, we have given the fastest algorithms. This is a very hard problem. It's what is called an NP-hard problem. So you can't have polynomial time algorithms, but we can have the next best that we have given. And couple of other problems which 3 minutes is too short to write, because there are also hardest questions on the earth on the slide. So I will skip that. Finally, I just moved to some engineering problems which I have been interested in the last couple of years. So which is related to mainly cryptography and learning theory. So cryptography is actually used in algebra extensively. This is probably the only method by which you can make systems secure, and you can transmit information even in the presence of errors. So these are mainly methods based on number theory, algebra, multivariate systems, like multivariate cryptography is there, and curves, for example, hyperelliptic curves. There is a cryptographic protocol based on that, and also based on hyperelliptic curves. Second kind of problems are to do with what is called in AI the artificial neural network. This again is essentially a circuit where every gate is doing some real computation, and there are layers. So the more gates you add and the more layers you add, you can make decision making for harder problems. Okay, so so basically AI uses circuits for decision making when there is no easy function that you can guess. So then this circuit is actually learned from the input. Okay, so as it was said very eloquently in the previous talk, that there is a big gap between 1,000 paper solutions and 200 billion population who is actually suffering. The twain shall never meet. So we are trying to make the twain meet. Okay, so there are theoretical solutions, and we have developed a center where we actually try to apply these at scale. So we try to solve government problems at scale. So you can see more about that on this website. Thanks.
So for the roots, you said that the number of multiplicity is exponential in what? In the n,
Yeah, right,
in the
right.
root, in the
Yeah, it was
degree?
not proper. The statement was not properly made. So you
Yeah.
have to look at a circuit,
Yes, yes.
which is, let's say, in n variables, and the
Yes.
circuit size is s.
Okay.
So the question we are interested in is, what can you say about the factors of the polynomial that this circuit computes?
Okay.
So now the factors are obviously again n-variate polynomials,
Right.
but they may have degree extremely high.
Okay.
and they may be very hard polynomials. That is, the circuit size may be 2 raised to s, and degree also may be 2 raised to s.
I see. I see.
So this is a general situation. I mean, you cannot bound the multiplicity, and you cannot also bound the size. So there are specific conjectures related to this situation which are open.
Okay.
And we made progress on them.
Thank you.
After the talk, I can tell you.
No, so I just wanted to know, I mean, as a person from mathematics, so if you, when you translate from circuits to algorithms, does the polynomial business translate, or there is some difference between them?
Yeah, so there is something called uniformity assumption. So what can happen is that theoretically we may say that a polynomial is easy because for any given input size n, n number of variables, circuits do exist, but then they may exist in a very different way as you change n. So in practice, nobody can actually fabricate it. Fabrication may be very expensive. So for fabrication possibility, there is a uniformity assumption. We say that, well, circuits exist and they can also be computed. So then somebody can actually fabricate them for whatever n you want. Most of the natural problems are of this type.
Okay.
Yeah.
Hi.
Last question, please.
Okay. So you made a statement about removing a number of the preconditions that govern the classical Newton algorithm. Now, the classical Newton algorithm is an iterative process. The iteration is kind of essential to the process, and the halt is determined by how much accuracy you are willing to tolerate.
Yes.
But then you actually talked about embedding this into algebraic computation.
Yes.
So there's obviously some conceptual input that you didn't talk about.
Yes. So
is it possible to talk about it in like one line, if at all possible?
So the conceptual input for you is instead of looking at real numbers like digits in decimals, you should think of the formal power series of the multivariate polynomial ring. So you have to look at the x1 dot dot xn. If that is your ideal, you have to look at this ideal adic power series, and then your notion of convergence changes. So instead of the numbers getting smaller, we say that the degree is getting higher. So in that sense, our iteration will stop.
Yeah.
Or truncate.
Okay. Thank you very much. It's an exciting talk. Let us give him a big hand.
Thank you.